Suppose we have a situation where it's raining and the rainfall speed is 5 meters per second, and suppose you are traveling in your bike at 12 meters per second towards the right. The question is, in what direction should you hold your umbrella? At first, this sounds like a random and an absurd question. I mean, it's reasonable to ask, why can't we just hold our umbrella this way? Just like normal, right? Well, if you hold your umbrella this way when you're traveling in a bike, you'll end up getting wet. It's easier to see that if we could just isolate one raindrop. Let's do that. Let's isolate one raindrop. Now this drop is falling down like this. Now if you were still on the ground, not moving, then that raindrop wouldn't have bothered you. However, remember, you are moving towards the right. So if you wait for some time, not only will the drop fall down, but in that time, you and your bike would have also gone forward to hit that raindrop. In other words, your front part of the bike could get wet because of this. And so that is not the direction in which you should hold your umbrella if you don't want to get wet. So let's put that umbrella down and let's think about this. The key now to solving this problem would be looking at things from the biker's perspective. All right. In other words, we have to look at the direction of the rainfall as seen from the bike or with respect to the bike. Ooh, do you see that this is really a question in disguise about relative motion? The real question is, what is the direction of the rainfall with respect to the bike or relative to the bike? So we need to now jump into the bike's perspective and look at things. And we've already done one video on relative motion in 2 dimensions. And if you have not watched that, it's better to first watch that and then come back over here. All right, so let's jump into the bike's point of view. Okay, this is my poor attempt of showing the bike's perspective. This is your arm, this is your shoulder. So excuse the drawing over here. What will it look like from the bike's point of view? Well, you don't see the bike moving. Instead, the rest of the world will go backwards. So you would see the ground going back. You'll also see the air going backwards. That's why you get the breeze and everything. And notice, since on the ground, the bike is going forward 12 meters per second. With respect to the bike, the ground is going backwards 12 meters per second. So keep that in mind. Okay, now let's look at what happens to a raindrop. Let's pick one raindrop over here. And also let's put a partition over here. Okay, super. We have to calculate what direction the raindrop falls from the bike's perspective. To do that, we'll wait for 1 second. So if we wait for 1 second, you'll see that this raindrop would fall down 5 meters because it's falling down 5 meters per second. So let's just write that down over here. So this would be 5 meters in 1 second. But remember, in that 1 second, the ground and the raindrop and the air, everything is going backwards 12 meters. So the whole thing goes back 12 meters. So let's put that as well. So the whole thing would go 12 meters back in 1 second. And so now you can see that 1 second ago, the drop was here. Now it's over here. So as seen from the bike, the raindrop doesn't fall straight down, but instead it goes this way. So this means, as seen from the bike, the rainfall is no longer happening downwards. It's happening at an angle like this. And this could be a very familiar situation. If you've ever been in a car or a bus while it was raining, and if you looked outside, you would really see that the raindrops no longer fall vertically down, but instead they'll be angled a little backwards. Okay. All right, so our goal now is to calculate what this angle is going to be. So let's do that. What is this angle equal to? Let's call this angle as alpha. And we can calculate this using trigonometry. This is a right angle triangle. We know the opposite side. We know the adjacent side. Which ratio connects opposite side and adjacent side? Ooh, tan. So we can say tan alpha is equal to the opposite side. So that's 12 divided by the adjacent side divided by 5. So that gives us 2.4. And so alpha will be equal to tan inverse of 2.4. And if you look up a trigonometry table, this angle turns out to be roughly 67.4 degrees. And so now we know exactly at what angle the rainfall is happening from the bike's perspective. And so from the bike's perspective, the rainfall might look somewhat like this, somewhat this way. This is what it looks like. And it's for that reason, if you have to hold your umbrella, it should be pointed a little bit forward. And since we know this angle over here, the rainfall is making an angle of alpha, 67.4 degrees with respect to the vertical, you must also hold your umbrella at that same angle forward. So you should tilt your umbrella at the same angle alpha forward. And there's our solution. Now, one small note, we could have arrived at this result directly by using the general expression that we derived in a previous video, and that was the relative velocity of the rain with respect to the bike. That is equal to the velocity of the rain as seen from the ground minus the velocity of the bike as seen from the ground. And if we had used this expression, we would get the same result. Let's see. We are adding VR, so over here there's VR, and the negative of VB. Well, VB is 12 meters per second forward, so negative of that would be 12 meters per second backward, see? So when you add this, you get this vector, so we get the same result. Another thing we could understand over here is you could calculate this length. If you use Pythagoras theorem, then this is the hypotenuse. The hypotenuse would be equal to, things are getting crowded, the hypotenuse is equal to 12 squared plus 5 squared, Pythagoras, that's going to be 13. So this length would be 13, which means that the rain would travel 13 meters this way in 1 second, which means from your perspective, the rainfall is happening at 13 meters per second. It's more than double the velocity as seen from the ground. And so this could really hurt you. So traveling very fast in the rainfall may not be a great idea.